electronics scene specifically, I think that I use tenses more like, this is how a credit word works. Notice how this is how electricity runs through, like when you plug in components. And so I guess the tense is like present tense, because you're also using words for encouragement. Like, now that we know this, you can do this as well.
Kind of like a we.
Yeah.
Thank you.
I'm Etienne and I'm here to present non-planar ironing. Basically, this is a new technique in 3D printing that we've developed. So a little bit of just kind of the fundamentals of 3D printing, make sure we're on the same page. Basically, if you've got a 3D model, which looks like the one there on the right, you have like a thin, like if you have a slight slope, you end up having really jagged layer lines, right? It goes like up, but because it goes up a little bit, it like shoots off to the side a lot, and you end up having these really, really ugly slopes. You can improve that by having thinner layers, but having thinner layers means that you take way longer to actually print something, and it still has quite a jagged slope. And this causes quite a few issues, right? So, for example, if you're trying to design an airfoil, then you've got these jagged lines, so it's awful for aerodynamics. Or if you're trying to make something easy to clean, now you've got all these little holes for whatever food or whatever you're trying to clean off of it to get into, and it's not great. But there's one benefit of it, which is it's easy to process, right? You just take your model, put it into, like, that's what's called slicing, right? Conversion to G-code. You just slice it into layers, and then you easy, done. Also, yeah, it's awful for things like friction and stuff like that. So, there's a non-existent image. Basically, there's been two techniques that we've combined to try to fix this issue. The first thing is non-planar printing or curved layer printing with dynamic z-axis. That's been explored in a whole bunch of different papers, a whole bunch of different times. But basically, instead of going layer by layer by layer, you go layer by layer and then not by layer. I'll show you an image of that in a moment, and then the next thing is ironing, right? Which is basically going over your part again without extruding any more material to remelt the last layer together. And that creates a much smoother surface. The non-existent image is the one I need for explaining. So layer by layer, and then the last layer is at an angle, right? So it still is jagged, but because the surface that would be jagged on is like perpendicular to the angle you're printing at, it ends up being a lot smoother. What we did is we tried to combine these two techniques. Basically, you take your sliced model and you get like these points along the side, and from those points you're able to create kind of a zigzag pattern, which goes all the way just back and forth between this whole thing. That looks a little bit like this, right? So you take your top layer, you create this whole big zigzag pattern, and I created a bunch of Python code to do that, and then you just merge it back into the G code, and now it's ready to print. Only a few differences is, there's the step over distance, right? How much of a zigzag it is. Like, do we go like this, or do we go like this? Is it offset, and a whole bunch of different parameters that we kind of test out. Wow, it really does not like these images. That is less than helpful for explaining. So we're trying to do a few different things, right? So normally in ironing, because you're remelting the parts together, there's like some very, very small holes. So we thought maybe if we add a little bit of extrusion, we can help fill in those small holes. Turns out, well, doesn't really help that much. It just means that you have more filament and more material that's just squeezed off to the side. The next thing is the step over distance. So again, how much would you step over? We found that 0.01 millimeters was good. That number can probably be refined a little bit to kind of optimize it. If it's higher than that, you don't have it as smooth. If it's lower than that, it just takes longer and it's the same level of smoothness, right? And then the last thing is the Z offset. So do you gouge the part by putting the nozzle directly onto it and moving it back and forth, or should you offset it just a little bit to prevent that gouging? Turns out the gouging is fine. If you gouge it evenly, it ends up being smooth. Yeah, and if you lift it up, then it doesn't actually iron well enough. Yeah, so this is how well it worked. Normal 3D printing is the one on the left there, right? You can see the big steps. The previous best paper is the one in the middle of there. You can see it's significantly smoother, but it's still not perfectly smooth. And then our one is the one on the right over there. It looks like I turned the part over, to be honest. It's super, super smooth. If you want to see, I've got some samples over here, and you can see that actually the bottom layer is quite bad, so you can tell that it hasn't just been turned over. Yeah, so I've also done this at a very, very slight slope, because as we saw from the first slide, the slight slopes is where it's worst, right? If you've got a very steep part, it doesn't matter too much. But yeah, so we got some really, really good results. Unfortunately, I left my old university before I was able to take the final surface measurements. So I've got some colloquial measurements, but not enough to actually publish in the paper. We also tested this with a few different things. So we tested this with a curved part, and you can see that also worked quite well. So that part has got a convex and a concave curve. We also tested to see how high it could go. For the printer I was using, anything over about a 7 mil rise, this is over 20 millimeter run, ended up just hitting the nozzle, right? Hitting the actual extruder, which just means that it gets dislodged from the printer and you can't actually print. But if you kind of use a different printer or a different shape, then you can get that angle way, way higher, and it still seemed to work very well up to those high angles. Yep, so here's just a few more things. You're remelting the filament, right? Which means that you've got a lot of excess heat, and because you're going back and forth, it's more heat than it normally encounters. Which means that if you don't have a relatively high infill, it can start drooping down. So this is with about 5% infill. I was using generally about 15% infill, and that seems to support it enough. And the top one is just half smooth and half not. So you can see that it actually lowers the top surface by just a little bit when you remount it. Also, if especially using high angles, you do introduce a shear force, right? So you are pushing into the part, which means that it can get dislodged. So you need pretty good bed adhesion for it. Yeah, so some future research. If you're looking for a master's project, PhD project, or just a side project, please. I don't want to deal with this anymore. But there's some really interesting research to be done. Firstly, I just tested PLA. But yeah, so you can test ABS, ASA, PTG, all that kind of stuff. The next thing is nozzle temperature. I kept it at the previous nozzle temperature. I didn't change it at all. The next thing is nozzle geometry. The thing that I was really worried about going into this research was 3D printed nozzles look like this, right? You have got one point touching the print at any time, and I was really worried that that was going to, again, create very big gouges, which turns out it didn't. But maybe if you have a curved one, then you are always ironing perpendicular to the part, right? And you can make that just with an acorn nut and just drilling into the bottom, the way old wrap printers were made. Yeah, and then you can theoretically, maybe, I don't know, someone's got to do the research, do some good smoothing. Also, variable infill density, again, because you need a relatively, 15% infill to actually support it, right? So if you do variable infill, so it starts at 5% and works its way up to 15%, then it should be more supported and take less time, all that kind of stuff. And then printing speeds, just trying to kind of optimize this whole thing. Yeah, and references. Also, all the code's available. It's over there, github.com/Etienne/non-planar ironing. It is not commercially ready, so you have to use like the Python script and all that kind of stuff. But if you want to use it, or you want to develop future research or whatever, you can go there. Cool, thank you very much. Any questions? Yes? I'm not ironing between the layers, I'm ironing on the kind of curved top surface. So instead of ironing there, I'm ironing like that.
I meant like in the Jeep though, is it like put down a layer of iron?
No, it's put on layer, put on layer, put on layer, put on curved layer, or like a layer perpendicular to the surface, you know, and then ironing that top layer. Yes?
What was the time increase?
The time increase, very good question. So the time increase is, it depends, it scales on the part, right? So normally if you do like thinner layers, that scales almost like a cube.
Yes.
This scales
Yeah.
only with a like square layer.
Yes, parameters, yes.
So for these, like these samples I've got over here, which you won't be able to see.
From the quantum realm.
It was about 1 minute, maybe 2 minutes. Yes. Cool.
So you sound like the different geometries for the ironing. So some virtual extrudes
Mhm.
with your G code, or you see one extrude and they get a G code to switch to another one that's got an iron and attachment, or maybe even not just an attachment, maybe even like hot air or infrared or any other technique as a post-process head.
It's a very good question. I haven't thought of hot air or infrared, but we have thought of changing over to like a different extruder. Again, just changing over to like an acorn nut. Yeah, we have thought of that, but haven't really got around to testing it. But yeah, very good question. Seems like a good Yes.
I'm curious about the impact on like the nozzle lifespan and like change, anything or.
It was fine. Like the only thing is, again, you're introducing a bit of a shear force, right? Which means that the part can get slodged, especially if like you're trying to do a very, very steep part and now is hitting the extruder, right? And then in that case, it can theoretically get lodged and have whatever quick failure you have. So it's got a slightly higher chance of quick failure, but other than that. Yes, yeah, but I mean, obviously, if the quick failure is catastrophic, you can mess up. Yeah.
What was the largest size of print that you tested for?
Largest size. Good question. Probably about that big, and to be honest, that's because I accidentally like increased the size too much. Mainly because I was trying to just test as many different things as possible. Yeah, good question. Yes.
Yeah, I was wondering when you showed the image form with sags, when you were looking at infill, how many top layers are you using? Does it make a difference? Because with solvent smoothing on, I guess, and things, I tend top layers to give you a bit more strength in it.
Yeah.
Did that help?
Yes, exactly. Yeah. Also tested that. So this is like 5% infill with one top layer. Bad idea. But if you do 2 or 3 top layers, it's really, really good. But yeah, so if you do about 2 top layers with 5%, then you don't have the holes, but you still do have a little bit of drooping. But yeah, so I found about 2 to 3 with 15% is really good. Good question. Yes.
Did you see a lot of, like when the nozzle is contacting the filament, is it dragging the filament along with it as it melts it? And if so, how do you avoid doing that in your effort?
Yeah, so it does kind of drag it around, but that works well because it smooths over the whole thing. If you have a look at these when you're done, you should see that there's a very, very, very slight amount that kind of bulges over the edge because like it drags it slightly over. But to be honest, you have to really squint. You might need to like take a zoomed in photograph to actually see the effect. But yes, so it does drag it around, but works quite well because it drags around evenly.
One more question?
Did you compare the dimensional difference between the smooth part and the actual design?
I have not compared them. It's quite difficult for well, we, like, again, I had the equipment remotely and then kind of left before I was able to test things like surface roughness and that kind of stuff. But they seem like, comparing them to the other parts, quite dimensionally accurate. But also, yeah, you can't quite use exactly calipers, right? Because it's at, a 3-degree angle and stuff like that, so it's quite difficult to take that. But yeah, good question.
Thank you.
I'll pass it over to Amy for our next session.
We should what?
Take a bite.
Yeah.
Consent.
Yeah. All right. So, explain what we're doing today, Ollie.
That was the quantum curvature.
Quantum curvature.
But you used the word quantum.
We are in the quantum realm.
Yeah. Right. Well, we were